All right, welcome to the Explainer. Today we're going to dive into a really wild statistical mystery. It's a case where the data doesn't just lie to you, it tells two completely opposite stories at the very same time. So, to see how this works, let's start with a really puzzling case from a university's admission data. Now, at first glance, the answer to this question, well, it seems pretty obvious, right? Or is it? Okay, so when you just look at the big overall numbers, what we call the aggregate data, it seems super clear. Men are getting accepted at a higher rate than women. Seems like a pretty open and shut case of bias. Case closed, right? But, that is not the whole story. Not even close. In fact, if we just dig down one single level deeper, we find out the truth is the complete opposite. And boom, this is where the paradox hits you. When we slice the data by how competitive the departments are, something just shocking happens. Look at this. In the really tough competitive departments, women actually have a higher acceptance rate. Okay. And then the less competitive ones? Women also have a higher acceptance rate. So, wait a minute, how on earth can they be doing better in every single category, but somehow worse when you add it all up?
This mind-bending effect actually has a name, and to really get it, we've got to go find the hidden culprit that's lurking inside our data.
It's called Simpson's paradox. And it's basically what happens when we get tricked by those big combined numbers. It's when the simple grand total tells you one story, but the smaller detailed groups, they tell you the exact opposite. So what causes this? Well, the paradox is always caused by something statisticians call a confounding variable. And you can just think of it like a secret third party, It's the hidden force pulling the strings behind the scenes, totally messing up the real relationship between the two things we thought we were looking at. Okay, so let's put it all together and solve this university mystery. The confounding variable, our hidden culprit, was how competitive the departments were. Here's what happened. 1, women as a group tended to apply to the absolute toughest departments. 2, those super competitive departments, well, they just have lower acceptance rates for everybody. It's harder to get in. So because a bigger chunk of the female applicants were trying for these really hard to get into programs, it just dragged their overall average way down. It created a total illusion of bias. All right, now let's talk about where else this crazy paradox shows up. Because trust me, this is not just some weird statistical quirk you only find in university data. This illusion is hiding pretty much everywhere.
Yeah, it pops up in medicine all the time. So imagine this. You've got 2 treatments, and overall it looks like treatment B is the clear winner, right? It has a better recovery rate. But then the doctors decide to slice the data. They look at patients with mild cases and patients with severe cases separately. And what do they find? Treatment A is actually better for the mild cases, and it's better for the severe cases too. The paradox was hiding the real story. The sickest patients, who were less likely to recover anyway, were the ones getting treatment A.
And get this, it even shows up in sports. It's totally possible for a baseball player, let's call him player 1, to have a better batting average than player 2 every single year of their careers. And yet somehow, when you look at their overall career average, player 2's is higher. How's that possible? Well, the confounding variable, the hidden factor, was the number of times each player went up to bat in those different seasons.
Okay, so now that we've seen this problem in action, and we know how it can disguise itself, the big question is, how do we fight back? How do we not get fooled? Well, here's a simple toolkit for you to start thinking like a real data detective. The most important thing, really, is to get a little skeptical of those simple, big-picture numbers. Anytime you see a grand total or an average, just pause for a second. Ask yourself these 3 questions. First, what smaller groups are being mashed together to create this big number? Second, could there be some hidden factor out there that affects these groups in different ways? And third, what would the data actually look like if we tried to split it up by that factor? Honestly, it all boils down to one key action. You've got to stratify your data. Now, that's just a fancy word for slicing it up. Before you jump to any big conclusions, just try breaking the data down. Slice it by age, by location, by time, by severity, whatever makes sense. And then, see if the story still holds up. And look, this isn't just some fun brain teaser for stats nerds, okay? Ignoring this paradox, just blindly trusting those misleading averages, it can have some really serious real-world consequences. Think about it. In medicine, we could end up picking the worst treatment. In education, we might slap a failing label on a school that's actually doing a great job with its students. Or in public policy, a program that's genuinely working for every single group it's meant to help, it might get shut down just because the overall average looked bad. Making huge decisions based on this kind of misleading data can lead to some truly terrible outcomes.
And all of this reveals a really deep truth about numbers. Data isn't this objective, perfect thing that just speaks for itself. No, data tells a story. And the way we choose to group it, the way we aggregate it, that choice is what writes the story.
So what's the big takeaway here? It's this. Always, always question the simple story. The next time you see a headline or a chart or a report that gives you a nice, clean, simple average, challenge it. Ask yourself, okay, what groups are being combined here? What could be hiding underneath? Because more often than not, the real story, the more complicated, more interesting truth is waiting for you just one level deeper.